Yeah.
Right, we're going live, so our audience is now, well, this chat is now to the public.
Sounds good.
Let me know if you can see that the live stream's coming up, because I know there'll be a delay.
Yeah.
Right, we're going live, so our audience is now. I can hear that. There'll be an echo.
Sounds good.
Right, so just wait until the dot, and we'll hope the viewers goes up. It typically does. We don't know though, because it's the second year we've run this, so fingers crossed. Okay, so welcome everyone. Good morning, good afternoon, good evening, wherever you are in the world. Welcome to the second Reddit Robotics Showcase, an event for members of all ages and ability who have a passion for robotics around the world to share and discuss their enthusiasm for their projects, whether it be a work in progress or a finished piece of academic science. This is for everyone to share that. You can find out more about the event that's going on from the website, redditroboticsshowcase.com or wordpress.com, Google it. But now I'll hand over to our first keynote speaker for our first session on industrial and automation. Please welcome Matt Whelan, who's talking about the Ocado Series 600 bot.
Thanks, Oliver. Great to be here with everyone today. Let me just get my screen share going. All right, can you see that? Can I get a thumbs up from Oliver if the slides are up on screen for you? Fantastic. Okay, so hi everyone. My name's Matt. I'm head of engineering for the 600 series bot here at Ocado Technology. I'm going to cover a range of things today. Even by covering a range of things, I'm only going to touch on a little fraction of all of the robotics work that actually goes on in Ocado Technology. So you'll have to invite us back for another chat if you want to see some more of what we're up to. While I was prepping for this, I had a look at the WordPress site, and I've highlighted here everything that we actually do at Ocado Technology for different reasons and in different projects, but we cover a surprising range of the complete field of robotics that's been described. So today we'll primarily be talking about the one down the bottom, that's commercial and industrial robotics. That inherently covers things like mechatronic design and various bits of control as well. So we'll touch on those in a bit more detail, but we can dive into anything else in the questions if you'd like to ask some more. We'll also be talking a lot about 3D printing. So fans of Joel Telling of 3D printing nerd fame, or James Bruton of James Bruton fame, this one's for you. So a bit of history. Who are we? So our journey began some 22 years ago, back in 2000. A town called Hatfield in the United Kingdom. Our founders set up a business, and the idea was to change the way the world shops by putting groceries online and removing a whole chore from your life. Now, that is easier said than done. Let's talk about the challenge that we're trying to solve here. So we need a massive range. We need 50-odd thousand different items to be available to you, because if we don't stock that special thing that you like, you will go elsewhere for your whole order. We can't take just a part of your grocery basket. We've got to give you everything you need. And these products themselves are quite challenging. So some of them need to be in the refrigerator, some need to be in the freezer. You want to be able to order wonderful fresh strawberries from us. You don't want us to stick your milk and water on top of them and squash them all. You definitely don't want us to pack them in with bleach. And we have to get this whole thing executed at exactly the right time, because we can't leave it on your doorstep melting either. It needs to arrive when you ask for it so that you can be home to actually get it into your home and store it. So it's a pretty big logistics challenge. And there's a huge amount of technology that we use to solve this problem, right? A lot of it's out in the real world. So this is showing some of our routing algorithms. This is how we're optimizing which van is going to take which box to which customer. And we're re-optimizing this as a live algorithm every time that you make a change on the website. So this is a massive software system. It's incredibly advanced, and you have to have great systems from end to end to get this shopping in the customer's house. So you've got to have a great mobile app, you've got to have a great web store, huge amount of things that happen out in the real world, but we'll be talking about what happens inside the facility where these orders are actually fulfilled. So this is how we used to do it. This is lots and lots of conveyors and lifts and shuttles from MHE providers all over the world. And actually, the true story is that this is how we used to do it. We actually had a monorail system that looks a lot like an automotive production line, but I don't have any photos of that. It wasn't very good. So let's talk about the one just after. So we became fantastic system integrators, right? Because we had to scale up this grocery capability with the range and the speed and everything else that you need. And we had to do that competing with bricks and mortar stores where all of their customers do the picking and packing themselves and the delivery, because they drive to the shop and they collect what they want and take it home. So to compete, we had to have massive efficiencies. And that's where the automation comes in and why we've been growing this deep technical expertise over the last 20 odd years. So on the left, you see a big kind of lift and shuttle system that stores a massive kind of cube of boxes. And it's a random access system, so we can get fast moving items out of there. And then on the right, we've got all these conveyors, and we would have dozens of kilometers of conveyors in a single facility. I've actually got a short video to show you what that looks like. So this is a simulation of customer boxes. Each one of those little blue boxes would have 3 bags in it for your shopping, and it travels around this warehouse. This is a 4-story warehouse, and you've had the floors taken out in this visualization. And you can see all those boxes going around the aisles, just like you would in a supermarket, to collect the items they want. And we would do software in the loop simulation testing. So you see here some colors for analytics and different things that we want to measure. And we built 2 of these facilities, and they're phenomenally successful. So that's all cool, but there's no robots in them, right? So why am I talking about them? Well, I need to give you a little bit of the background of what the challenges are with that type of system for the robots to all make sense. So let's look at that video again. What happens if a single piece of that conveyor breaks? Well, that might block the only way that you can get from where you are to where you need to be. So that can cause a huge backup in the system. It either gives you a risk of stopping production, or it means you have to pay a lot of money to create redundant routing through your system. So that's one challenge. The other, and perhaps more important, is that this system takes quite a long time to travel through. So these boxes are doing what you do in a supermarket. They're going around the aisles and getting the products they want. But it can take more than 2 hours for one of those boxes to go from the point where it's put in the system to when it's ready to be loaded onto a van to come to your house. So if you want to get close to the customer and start offering immediacy and start getting to these services where you can say, I want my groceries, and they turn up less than half an hour later, then it's largely impossible with this type of system. So we moved on to something new. So this is what we do now. On the right-hand side, you will see our 500 series bot. So this is our current flagship product, and is not the one we're largely going to be talking about today. But you'll see it driving around a large grid structure, and underneath it, in these white boxes, are all the products that we need. So these boxes have got a hoist system inside. They can lower that hoist, collect the box into an internal cavity, and drive it to where we need it to be. And typically that means dropping it into what we call a peripheral device, which is essentially all of the human machine interfaces for this large system. So on the left here, you'll see the types of business processes going on. We've got stock arriving from our suppliers, and we might have 5,000 cans of soda turn up, and we're going to unpack all of that into our storage boxes, and then one of the bots is going to load it into the hive. We've got all of the interfacing with the delivery boxes as well. So we have stuff coming back from customers and going out to customers. These Tims and Toms, that stands for tote in machine, tote out machine. And then where the real magic happens is at the pick station. So this is where these robots are being commanded and choreographed to bring everything that you need to go in your box over to a pick station at the same time as your box is there. And that allows us, with either a human or a robotic operator, to actually complete the pick process. So that's where everything gets put in your bag, and then when your order's complete, it's picked up and taken over to a Tom or some other device that's going to outload that box and send it off in a van. So that's what we're doing with our core product, roboticizing the workings of our CFCs, our fulfillment centers. So this is a simulation to give you a sense of the scale. This is a relatively small grid. We've got much bigger ones, but you could see all those little colored boxes. Those are actually the bots driving around. And this is one of my favorite visualizations. So on top of the grid, you can see the plan. So this is all of the paths that are planned in by the central control system for these robots to actually go and do. And the Z-axis is time. So the further up above the grid you're looking, the further into the future you're seeing in the plan. So this whole thing's actually slowly descending towards the grid as time ticks on. And all the paths are colored by the type of work that we're doing. So you'll see the light green path where we're collecting stock and bringing it over to go in your bag. And you'll see these little yellow towers where we're perhaps digging boxes out of the way to get to that target bin that we need so that we can get what you've asked for. And then these are the pick stations that I mentioned before. So the customer boxes are queued up on the red conveyor. And then you can see the flurry of activity on either side as all of these boxes are brought down onto the green conveyor where those products are then presented to, again, the human or robotic operator so we can complete the pick operation. So this is what the big system looks like. And it begs the question, is this 500 series bot a robot? And I'm curious to hear people's thoughts on this. We're going to have a chat in the comments later. This machine has sensors on board. It can drive itself around and it can communicate. It can do lots of things that you would say a robot can do, but it also has no idea about any of the other robots around it because it's centrally controlled. So I call these semi-autonomous, these bots. But you could argue that this is also a mobile robot. And this is something that Tom Scott actually put at the end of his video that he did about us. You should go have a look at that. It's great if you want to see it. His argument was that each one of these robots could be considered an actuator in one giant robot, which I think is pretty cool. It means this is probably the biggest robot in the world, what you're seeing on the left here. So this is our site in Erith, and this has thousands of these robots operating on grids that are over 200 meters long. It's an absolutely phenomenal system, and if you ever get a chance to go and see it, I can't recommend it enough. So you can choose, you can pick your lens today, whether you think we're talking about an actuator or a robot or something else, or maybe we're just talking about 3D printing. It's up to you, but I'm going to go into a bit of detail on it, and you can ask any questions that you're interested in at the end. So this is the 600 series bot, and it doesn't look anything like the ones you saw in the previous videos. So this bot is made from 3D printed parts and carbon fiber. That is actually the majority of the bot. It's 3D printed parts of carbon fiber. You know, you add in a battery and some motors and some bits and pieces, but the structure and most of the mechanisms are all additively manufactured. So why is that useful? Well, it actually lets us massively reduce the weight of the machine. So this weighs a quarter or slightly less than a quarter of its predecessor. And that's got huge benefits for our business. So as I'll talk about in a moment, it probably makes the robot quite a lot cheaper, but there's more to it than that, because the grid structure that it needs to operate on doesn't have to withstand as large forces. So we can simplify that grid and we can make it quicker to install. We don't need to be on a special floor anymore because all of the loadings have gone down. So we can move into existing buildings. We can deploy closer to the customer and faster for our retail partners. So this is really, really important. Now, on the screen here, you can see some of the work that we do in topology optimization. And this is part of how we actually achieve this low weight. So a lot of the parts on the robot are actually algorithmically designed. And that has a double benefit when working with additive, because not only is it light, which is great for the reasons I've described, but it also makes it cheaper. The less material you use in additive, the less the part costs. So that's pretty exciting as well. So let's talk a little bit more about this. Why was it so important to get the weight down? When we started the R&D that led to the 600, we were actually looking at a slightly different application. We weren't specifically looking at a successor to the 500 series bot. We started with a lightweight first approach and quickly realized that this had some pretty substantial knock-on benefits, as I've described. So we ended up designing everything lightweight, and that allowed us to do some cool stuff, because when you make the bot a bit lighter, you don't need as big a motor to drive it around anymore. So now that motor is lighter as well, and it doesn't need as much power. So now I don't need as big a battery, and the battery's lighter and cheaper and smaller, and I can pack everything in nice and neatly. And you get through this virtuous circle where by starting light and having that approach, you actually pull the weight down even further, and you can kind of go around a few cycles of that. And that's how we've ended up. We haven't knocked off 10%. Again, as I mentioned, we were about a quarter of the way. So this is a profoundly different architecture for this type of industrial robot. And that's why it's so exciting to use additive in this way to get this kind of outcome. The other thing is where additive is right now. So this is the Gartner hype cycle prediction. It came out in 2019, data from 2018, and this is 3D printing predictions, right? You might have seen these hype cycles before. People get really excited. There's loads of press coverage. It actually takes a while for new technology to become real and useful. So you have this trough of disillusionment, and then eventually people start really exploiting it. So this is the stuff that we use, right? We're using powder bed fusion, material jetting, and extrusion. So those are the three of the big types of 3D printing. And you can see the powder bed fusion's quite far over to the left. I actually disagree with its position. I think it's one of the more mature technologies in additive, but it's still in the kind of 5 to 10 years kind of time frame, right? And here's some stuff that we do. So 3D printing and manufacturing, tooling, and just general enterprise 3D printing actually starting to make an impact on large businesses. So you'll note this is all kind of over to the right-hand side of the graph. But I mean, this is 4 years old. So I think most of these things are actually quite a lot further on than Gartner predicted. So it's quite well timed that we started looking at this lightweight design just as the possibility to move into scale manufacture with additive, which is what we intend to do, was becoming possible. So the technology is really real now, right? And it also just so happened that the guy who got the gig to actually run the department to design this thing had a small amount of enthusiasm for the technology. So this is my RepRap Huxley that I built from a kit that my brother bought me for Christmas back in 2014. I think this is it homing its motors for the first time. And this is me modestly taking it to the office 4 days later to show it off to my colleagues and using it in all kinds of silly ways from then on. So I've thought that this technology is fantastic for ages. It's never had anything to do with my work until the 600 series started. I was actually a software developer at the time this was happening, and I've only moved quite recently into this hardware and mechatronics space. So what can you actually do with it, right? Why can it unlock things that you can't do elsewhere? And why does that give us an edge for 600? Well, have a look at this part. You cannot make this part any other way than additive. You can't machine this part. You can't cast this part. You can't injection mold this part. So there's only one way to make it. Now, people have done bits of topology optimization before. We'll all have seen, cool examples of a bracket that was previously a big cast part, and then it was turned into this wonderful web-like structure, or something for really cool use cases in aerospace and this type of thing. We're doing something that's a bit further on than that. So if you look at this part, it's got about 20 odd functions, right? There's all kinds of things mounted to it. It's going to have bearings and motors and different things going on. And it's an integral part of our structure. And it's optimized perfectly for the load cases that it actually has to withstand. So we get massive part reductions by sort of throwing lots of things together into these large structures. And then most importantly, we get the weight and cost reductions that come with that optimal use of material to solve the problem. So that's pretty cool, right? But we're going to make a whole machine with this stuff. There's going to be 500-ish printed parts in this this robot when we launch it. About half of its weight is going to be 3D printed nylon. And can you really do that for an actual machine in an industrial environment? So can you match the precision and repeatability of a CNC? No, of course you can't. It's 3D printing. It's the most advanced printers that you can get. That's typically around the sort of 30, 40 micron range in terms of the most precise dimensions they can achieve. And most of the printers that are economic to use don't achieve that. Well, is it cheaper? Is it as cheap as mass manufacturing techniques like injection molding or die casting or other things that you see in large scale products? It is not. So why are we actually using it? Well, there's three things, and we'll talk a little bit about each. So design freedom, by far the most important. That's what allows you to do things like topology optimization in the first place. Time to market and change. So design freedom. We have designed hundreds of additively manufacturable parts. And one thing that's really clear is that you can design them for the function that you want them to do, and then they're either perfect out the box, or they need some small amount of tweaking to allow them to print well, maybe by orienting them a certain way, or by moving a bit of material because you've got something that's too thick and too much thermal mass. Generally speaking, you're never going back to the drawing board because the manufacturing process can't actually make it do the thing you want it to do. I think that's quite common in other types of manufacture. You come up with something conceptually and then you realize that it doesn't match your selected manufacturing technique. So you have to go and rethink or change material or do some other kind of more profound change. We just don't find that in our development, and it's incredibly powerful when you're trying to iterate versions of the product. You're a little bit more constrained in FDM printing than powder printing because you've got to think of support material and other stuff, but even so, it doesn't take much to figure out how to get these parts to actually work. So that's pretty cool. Time to market for us is critical. So we have to get from the idea that we've had to a prototype that proves that it's going to do the thing we need to something that's in scale manufacture. And we have to shorten the time between all of those phases. Now, the 600 series is a real step change. So there's all of these huge commercial benefits that I described around getting into new types of building and new propositions for our retail partners and our customers. So we're actually going to pioneer this new way of manufacturing because it's going to get us there faster. So we'll be building one of the largest print farms in the world, and we will be deploying this at scale to make an awful lot of these machines. There's going to be 50 or so of these large automated facilities deployed around the world in the next couple of years. So there'll be tens of thousands of machines in operation. So anything that can get us faster to where we need to be, because we have to catch up with ourselves as well. We are already a scaling business. So we want to move as fast as possible so that as we're deploying the sites that we've committed to, we can already exploit this fantastic new technology. So time to market is really key for us. And then there's change. So for a system that needs the reliability that ours does, because we have so many of these machines in operation, you have to accept that when you launch it, you're only going to have a small number of the machines, and the amount of data that you can harvest from them won't actually be that statistically significant. So when you're really, really trying to get into, you know, lots and lots of nines on your reliability numbers, you have to have quite a large fleet, and you expect that you're going to have to make some kind of change to it. How do you make that easier to do? Well, if you know most of the parts in your bill of materials are changed by simply sending a new digital file over to manufacture, that's actually profoundly different to what cutting and change looks like for other deployed products. So for research and academic settings, this might be less meaningful. It's just the prototyping capability is exciting. But for me, where I have to look after the whole life cycle of one of these products, I have to get it into operation and then make sure that it improves from there and it really hits the kind of targets that we've set ourselves, then that ability to change is phenomenally important. And then, of course, there's the development itself. So I imagine I'm preaching to the choir here. We probably have a lot of people who use 3D printing for some kind of robotics prototyping. It is absolutely core to the way that we've designed this bot. So we run 3-week sprint cycles where we can actually spin an entire new generation of the bot in that time if we need to. We can get the thing printed, get it built, test it, learn something, change it, and go again. And we do that relentlessly to get every single detail covered and really drive in the performance that we need. So I'm going to move topic a little bit now into some of the ways of working. So that's the product. You can ask any questions you like, and we can talk about that afterwards. The way that we actually developed this, we were a software company before we were a hardware company, and that, at least for me, because I was a software guy before I was a hardware guy, has changed our perception a little bit of how you can develop hardware. And I think this is really interesting for broader product development. So if you're in software, it is obvious to you, or at least becomes obvious to you very quickly after you start working in industry, that the type of stuff that I've got on screen here is really important, right? You have to have good, proper version control. So that would be Git for you if you're writing some code, and it would be Onshape for us in terms of the version control of our CAD. You need really, really good continuous integration. And if you're really good, then there's continuous deployment as well. And for us, that looks like having a complete manufacturable pack, you know, everything that you need to define your product and iterating that. So we're not going to go through a bunch of phases over here of something that's not ready and then wait 6 months to get everything prepared. You should always be iterating a deployable version of your product. You need good automation. For us, that's things as simple as I've got 500 printed parts. I don't want to right-click them all and hit export and try and count them into a big zip file to send to my printer. I'm going to need some scripting around that. We also have really mature tooling around how we pipe our CAD definitions into the topology optimization platform. And that allows us to change as rapidly as we need to while still doing this really advanced piece of design on the side. So we've actually kind of baked that in a largely automated way. And then custom tooling as well. So that can be things simple as how do I, make a little slot for a bearing to fit in my machine, but it can also be wider tooling around how you actually gear up towards manufacturing one of these products, because a lot of this is brand new and most of this has never been manufactured in this way before. So that's really, really important. And I think for a robotics audience, we can consider the fact that we're already pretty software rich, right? I expect that a lot of people who are on the call have got some kind of background in software, even if you're into a wider kind of mechatronics field. So don't underestimate the value of taking that software expertise and putting it into your hardware development practices. We found that to be incredibly powerful. So hopefully that's something we can take away today. Another thing is just in your tooling choices. So this is just a bit of a lesson for us. We have an international department, right? So half my team's here in Stockholm, where I'm today, the other half's in the UK. And using tooling that allows you to collaborate is incredibly important. But a lot of people don't necessarily know that the most modern tooling is profoundly better at this than some of the incumbents. So does your CAD platform let you actually collaborate in real time on a design from different locations? Most of them don't. Most of them you have to check a file out if you're using some central repository, and then that blocks it from anyone else working on it. There are tools, so we use Onshape, there are others. There are tools that let you actually collaborate in real time, see everyone's changes as they happen, make everything visible. It's really common for us in the office here. We will have people pair CADing, which is another sort of bit of methodology we pulled over from software. So you usually have a bunch of Onshape windows up where you're modeling your robot, and you'll have someone in a Google Hangout, in our case, on the other screen, perhaps in another development center in another country. It's a completely natural part of how we collaborate. So I would recommend you go look at those things as well. They are very central to our ability to move as fast as we do. So if any of that is of interest, or if you haven't worked in industry before, or if you perhaps wonder why hardware development is so slow in other bits of development, then here's a sort of a bit of a summary of these points. So you set up your tooling for collaboration. I think that is absolutely critical. You can then customize it for other bits of productivity or specialist features afterwards, as long as you have something extensible. So look for that in your tooling as well. Do more additive. This is robotics, right? It's probably got some of the largest adoption of additive already. You see so much on YouTube, incredible people making incredible things utilizing this technology. The thing that I think is changing, in fact, the thing I would argue has changed, is the road between having that prototype and having something that's actually ready for real deployment in the world is very small or gone now. That gap has closed, and that's incredibly exciting if you're doing development in this space. And all of that's going to help you go faster. So that's my little recommendation today, if you're interested. If you're annoyed that you haven't seen robot arms yet, again, I said I would only touch on a little fraction of what we do at Ocado. So this is another extraordinary bit of product development. It's being done by another team in Ocado Technology. This is called on-grid robotic pick. So this is using our machine learning powered robotic picking and packing capability deployed directly on top of one of our grid systems, coexisting with the 600 series bot. This is an absolutely extraordinary development that I'm not the right person to talk to you about today. And again, have us back next year. We'd love to talk to you about some more of the incredible things that are going on in the business. And if you're disappointed that that robot wasn't 3D printed, And the last thing I'll mention today is our good friends over at Haddington Dynamics. They joined the Ocado group recently, and those guys are developing this robot you see on screen here. So this is Dexter, and this is a robotic arm, which is largely 3D printed and made of carbon fiber. It probably has more in common with the 600 series bot than it has differences. They were developed completely independently. And there's some extraordinary technology here as well. There's FPGA-based encoder technology that drives incredible precision, even in this imprecise manufacturing method, as we discussed. It's another incredibly cool piece of technology. So I'd definitely recommend going and looking that up as well, or perhaps having someone come and talk next time. So hopefully that's been interesting. If you want to know more, then let's get some questions going. And if you really, really like it, you can, of course, come and work with us as well. So here's a QR code you can scan, come say hello, come join my team, come join the team developing the other robotics at Ocado. We'd love to talk to you about it. Thank you very much.
Thank you. That was absolutely fascinating, really enjoyable. As Michael has said in the chat, if you can post any questions that you have into the YouTube chat. If you're here joining us on the Zoom, you're welcome to actually unmute and you can ask a direct question directly, but of course for the general public via the stream. I would like to start, if that's okay, seeing as no one's floated one just yet. One thing that I noticed is that in the videos for the Ocado, they talk about how obviously they've gone to the effort of protecting it, mentioned something like over 200 patents. Now, my brain says it's very important to protect the millions of pounds of investment and all the hard work that goes into it. My heart says 3D printing, part optimization, carbon fiber shafts, what is there to patent? So can you give a bit of insight to how where the legal protection comes into it, how closely you're working with those kinds of people, influence, anything you'd like to share regarding that?
Sure. So IP protection is a really interesting thing, right? If you're going to make investment that can drive forward this type of technology, in the private commercial space, you've got to look after your interests. You don't want somebody to just come and copy paste what you're doing and get all of the benefits of your hard work without the investment. So we are very, very carefully protecting the work we do. It's typically application dependent, right? So we're not necessarily trying to say we just own the idea of 3D printing a thing. We're trying to say that the clever mechanisms that we've put in place to allow it to do this job as well as it does is a concept that we claim and own. So that's definitely quite a natural part of our ways of working. We collaborate really closely with our IP team because this is such a core product. I'm named inventor on quite a few patents that Ocado have filed. And we largely see that as quite a positive thing, where we sort of have a bit of ownership over the value, and we get some of our name on that shows the contribution that we've made. We are also contributing to various open source products across the business, right? So this isn't something that we just eschew generally. It is when we have the core value driving products within the business, we've got to make sure those are looked after. So that's quite a natural setup, I think, and probably quite common across the commercial space.
No, thank you. Yeah, I understand. At my master's, I had to do intellectual property landscape analysis.
Yeah.
So one question we've got, how many companies compete in this space and how do you manage to be competitive? I think a very good question, because I've seen a talk before from, I know Amazon are in this game too. You've got to compete against them. That's not an easy person to compete against.
Yeah, that's right.
How do you guys handle that kind of stuff?
So the material handling space in general is huge, and there are endless types of problems that you can solve in logistics in general. Where we are specialist is in the really, really high performance zone. So for all the reasons I mentioned at the start about how hard groceries are, and that's while operating in a market where the margins are razor thin, and as I mentioned, the incumbent gets free labor from the customer because they drive to the shop and pick all their own stuff. So you have to move products incredibly quickly and efficiently and reliably to be good enough to do groceries. And for a long part of our history, people thought that you couldn't be good enough to do groceries profitably. So we have a very, very fast system. And one of the things that's interesting with the 600 is that we also actually have a much cheaper system now, because this lightweight actually drives down these costs. So you may see that technology is applicable much more broadly in the future. But in terms of where we compete today, there aren't actually any other systems that I'm aware of that could do grocery at the efficiency that we're able to. So if you take Amazon Robotics, so you wrote that specifically. So Amazon Robotics was a fantastic product. There was an acquisition some years ago now of Kiva Robotics, who we actually did speak to a little bit back in the day. That's a wonderful product for a massively wide range of goods where you maybe want one or two. So if you think to your last Amazon order that you made, if you've made one, how many items were in your basket? It wasn't 50, right? Because a grocery order is around 50. So it's a fundamentally different type of problem it's trying to solve. But Amazon sell everything. So they want this huge warehouse and they want to have random access to this single SKU that maybe sells once a week or something. So those are a little bit different sweet spots that they're trying to solve. But certainly the bit where we feel that we have really got an edge on any of the competition is in this very high performance space. And that's what all of the series of our bot actually achieve. They all move around with the same performance characteristics, just that the 600 does so with these large reductions in weight and cost.
And that high performance extends as well to the development strategy of being able to say we can development faster than the competition as well.
That's right.
We can get a patent slapped on it as well quicker before that kind of stuff too.
Yes. So with the adoption of additive, we have a hill to climb, right? To deploy this at the scale that we intend to. It is a first of a kind product. There is nothing else like it. But we see this tipping point in the maturation of that technology, and we want to be miles ahead by the time that that tipping point tips. So that's sort of why we are so ambitious in our approach to deploying this at scale.
Okay, thank you. I think Michael's going to pitch a couple of questions.
Yeah, so the one question I had was kind of about how deep does the kind of custom approach go? You still have things like bearings and linear rails and motors and stuff, and there is some level of risk associated with making everything custom. You take on a lot more stuff that you would otherwise push off to whoever's supplying you the part. So just curious, how deep does that go? Is there still a lot of stuff that you're taking that's off the shelf? Or are you doing just everything as custom as it needs to be to get this thing as fast as possible?
Yeah. So you've picked up on a really important point about the sort of choices that we have to make in developing a product like this. So we categorically do not design our own ball bearings. I think the only people who should are ball bearing companies. The general model is we use 3D prints, carbon fiber, off-the-shelf components. That's kind of it. The exceptions are bits where things are always custom. So a motor, for example, you typically find a supplier who does the type of component that you want, but by the time you look at your actual application, there's always some customization that goes into it. And that's the same for batteries as well. So nearly every product you have with a battery, and there will have been a battery development project behind getting that thing to work. So there is some element of customization there, but there's definitely a preference for off-the-shelf, short lead time parts, because there's no point being able to change your design overnight with additive if you then wait 9 months to get another part through the door to actually implement a change. So yeah, the off-the-shelf in terms of fixtures, bearings, drive belts, all of that kind of thing that we use, and the customization is all about how you package and integrate all of those things into one structure that does the job.
Okay, thank you. We do have another question from YouTube, which is you did mention a 2-hour pick time in version 2 of your approach. What is your current pick time, just for comparison?
So we can pick a complete van route. So that's 80 totes with 3 bags in each in about 15 minutes across a work group of 4 stations. So you have to look at this with a slightly macro lens, but that will be some large number of robots doing lots and lots of things in parallel. And then all of those boxes coming to fulfill those picks. And then an entire sort of set of frames with 4 frames of 20 totes each being loaded into a van. That's about 15 minutes of operation for 4 of those pick stations. A very large site can have 100 plus pick stations for each temperature regime. So that's 100-ish in ambient, 100-ish in chill. So there's massive throughput in these sites. The sort of largest ones will be about 35 large supermarkets worth of throughput. But then with that latency that allows the immediacy offering. So that's kind of unrivaled.
All right, that seems to be it right now for the YouTube questions. Mark, I think you mentioned that you had a question you'd like to ask. Go ahead.
Yeah, thanks, Matt. Can you hear me all right?
Yeah.
Okay, cool. No, very interesting. And you've talked a lot about your fulfillment centers. I was wondering about the last mile delivery that Ocado is planning, because I've seen the partnership with Oxbotica that was announced fairly recently. Do you want to tell us a little bit more about that? What's the plans and how does that compete with the other big competitors as well? What your plans are, particularly with last mile delivery in the UK?
So I'm going to take the easy way out a little bit by saying I did say I wasn't the right person to answer some of the questions and such the breadth of work that goes on, but we clearly recognize that this is a really important piece of the puzzle, right? You can get phenomenally efficient at getting all of the groceries picked and packed, but you're always going to have some fixed costs to get it to a customer. So it's really important not to lose the benefit of all the efficiencies you have over here because someone else solved the problem over here. And maybe one's worth more than the other and all this kind of thing. So you've got to have the whole piece end to end, and we're always looking end to end. There are a bunch of other projects I could have mentioned around other pieces inside the CFC that we're automating, sort of taking out some of the worst jobs and the high labor parts. The last mile piece, we've got 2 partnerships. It's actually Oxbotica and Wave, and we are running some trials right now, sort of small local trials looking at where the technology has got to. We're developing specific instances of that technology that are optimized for groceries, so around how a device might look and kind of interface it might have with a customer, or other bits of automation, maybe even trying to get it up to the customer's door and this kind of thing. So we're absolutely looking across the entire spectrum, but this is one of the things that's on the list of you should get someone else to come and talk about it next time, because I'm by no means informed on the topic, I'm afraid.
That's all right. Thanks.
Interesting. I've got one more question, and I think then what we will do is we will simply take a pause. And for those watching via YouTube, that just means we'll be returning on the hour, and you'll be looking at a blank screen until then for our next presentation. So one final question is, how do your 600 series bots grasp soft products without squishing them? So obviously when you see those little grippers, it's often a cardboard box that's shown in the video. How do you grab a bag of crisps without, smashing everything up, or a piece of fruit without bruising it, those kinds of things?
Okay, so that's easy. We don't. So the 600 series bot and the 500 and the 400, they all do a single job. They pick up a predefined box and move it somewhere else. They are box moving machines. So there's two types of robotics, right? You can either have robotics where you design its environment to make it easy for the robot, or you can have robots that you try and put in the complex real world. And we do both, but they're different products. So the 600 works in a very tightly defined environment. It's on a precision engineered grid structure. Every single box is exactly the same, and it always wants to do the same job, but we want it to do it at incredibly high repeatability and reliability.
So what about the robot arm then? The one that...
So the robot arm, there's all kinds of research in that space. And again, I'm not the right expert for it, but we've done there's a couple of ways of picking up products. So we have suction cups for some things. That's actually quite good for some fruits. And we also have parallel jaw grippers. We're probably looking at deploying some kind of hybrid of those two because with breadth of range that we have to cover, neither one is a silver bullet. So it's probably some combination of the two. We've actually done quite a lot of fundamental research over the years as well, including some EU-funded research and partnerships with universities, looking at everything across the kind of grasping and manipulation spectrum. So sort of strategies for how you can pick up paper-thin objects by sliding them to the edge of a desk to get a grip on them, and all these types of things that are incredibly obvious to a human, but are surprisingly difficult to program in robotics. And I'm sure I'm talking to an audience that's familiar with this type of challenge. So lots and lots of work in that space. It's another one that I'm sure we'd be thrilled to come back and discuss in some more detail.
Fantastic. And one more quick one. How do you stop the robots from colliding with each other? And I think that's kind of referring to, as much, is that a decision that's handled by the individual or the larger factory, some kind of global communication individual? How do you go about that? Just making sure they don't bump into each other.
So this is why I asked, is it really a robot? And I'm curious to see what people think. The robot doesn't know why it's going where it's going, and it doesn't know what else is there. So it gets told to drive 40 cells in the positive X direction, and it does it at the exact time it's commanded to do it. The collision avoidance and all the optimization of what goes where is done by a central control system. And there's various clever ways that it makes it self-tolerant so that we don't have collisions. So for example, we will only release a little bit of a bot's path at once. So if we want it to drive 100 cells, we might initially tell it to drive 12. And when it's successfully done 6, and we've looked at all the other robots and no one's accidentally stopped in front of it, we'll release a bit more. So there's a sort of real-time comms loop there. So there's a big complex planning engine that actually determines both what's the best robot for the job, what's the best box to get this product, what's the fastest way there, heuristics to manage congestion, and all kinds of things. And that intelligence lives off-bot, which is why you could say, maybe it's not really a robot. Maybe it's an actuator, but that's for you to decide.
The rule of thumb that I generally try to use for anyone who's on the subreddit for moderating the posts is, if a child would look at it and go, look, a robot, then it's probably a robot. That's really as far as I go into it, because otherwise you get into such a grey area of tedious decision making. It's not worth the time. Cool.
I'll ask my little boy when I get home then.
Anyway, okay, thank you very much, everyone. And thank you, Matt. That was a fantastic keynote. Great way to start off a wonderful weekend of robotics. So the video will now be muted and the camera killed, but we'll be back on the hour in just under 15 minutes for our next presentation. Real power armor, hybrid active passive armor, HAPA. So look forward to that. And they're going to be giving a live demonstration. So a quick prayer for them. Okay, everyone, thank you very much. See you soon. I really enjoyed that keynote. I'm not just saying that because I'm live on camera. I really did. I thought it was really interesting.
I thought it was very interesting. Yeah, it's always great to see like new stuff like that, especially all of the topology optimization. I think it was wonderful.
Yeah, it's nice. It's a great to see it done right. I think a few of us have attempted topology optimization here and there. Now we've got a visual example of that's what we're aiming for, folks.
Yeah.
Anyway,
All right.
so, yep, go on.
I said we're almost up for Nye MechWorks.
Who gave a presentation last year as well. So a returning guest, second in a row. As soon as he's ready, they're ready to put on the camera. Just gonna wait for as soon as that camera pops up. I hope he's going okay. He was testing, audio and video before.
Yeah.
There's always the way for it to fail the moment it's needed. So if it was going to go wrong, it would go wrong now. That was what you expect.
No, I think he'll be good. He has some good demo stuff lined up.
Yeah.
And there he is. Perfect.
Okay, wonderful. We will hand over then.
Muting. Can you hear me? Am I live?
Yep, we can hear you fine, and you're spotlighted, so everyone should now be able to see you as well.
As Monty Python says, now for something completely different. Bit of a kitsch sort of thing going on with just making stuff out of science fiction instead of trying to find practical applications for robotics. So just having fun in my garage. Let's see here. So this is one of the second latest of my works. This little fellow right here is the latest. I'll explain her in a bit, but I suppose I should get to what everybody's been waiting for, which is demonstrating the power armor now. I'm just not sure if I'll be able to walk around because getting it off the rack is a little hinky. So we'll just go for it and see. And then I'll explain how it works and all that stuff in a very quick way afterwards if I don't get stuck inside. Yeah. I'm not wearing the right shoes, so I just gotta take those off. There we go. Got working arms.
Oh, I gotta say, that is fantastic.
And it looks like the foot clamps aren't working, so I don't think I'm going to be walking anywhere. But I can share some footage of that eventually. So, also got a helmet closed. And lights. Nope. Foot clamps are not on. Ah. I suppose that would be the live portion of the arms moving around and all that stuff. And I will be seeing if I can switch over to the video of it fully in action. Because, you know, the power armor things can be a little finicky. So we'll share my screen. Share that. There we go. It's all precision engineered, and if I don't wear the proper shoes, it's very hard to do any walking in it. Now, the important thing to bear in mind is that the correct paneling is just to test out the metal template. So it is not the actual material I plan on using for anything particularly useful. This is just something aesthetic that I'm doing because it's actually based off of the Halo Legends Yggdrasil armor from that cartoon released in, when was it, 2012? So, going for a bit of pop sci-fi sort of thing.
I'm very impressed at how it does, you know, look like you are moving relatively easy in it. I was expecting it to be a lot more difficult. How much of it is, you know, actuated by you versus, you know, is it hydraulics or electric?
It is all electrical. The arms have an electrical system in it, and the legs are passive, meaning that they've got springs and bungee cords, like a lot of the commercial exoskeletons you see running around.
Okay, wow. And so the hands as well. You've got these, you know, those aren't your hands, are they? Those are.
Nope.
So what about those? What's going on with them?
Well, those are placeholder toy robot hands until I figure out building some actual ones that can support weight. Because the arms themselves are capable of at least lifting 40 pounds when it's mounted on there properly. However, with little toy plastic hands, you know, you can't really lift much.
That might be something where you'd want to look at what else is out there in the open source community.
Yeah, okay, how do I stop sharing? Oh, there we go. Stop sharing the screen. There we go. So, really, the interesting thing about this is that there's no computers in it whatsoever. I can take off the chest panel and give it a little peek at least some of the stuff that lies within.
So then how is it measuring input then? When you're moving and it's supporting you, is that done through measuring the motor resistance or just switch presses?
It uses, let's see, I've got some of them right here. Automotive relays. So they're double pull, double throw. You know, run current in them. You know, makes the motor go one way. Put it through both the coil and the input, makes the motor rotate the other way.
But then so when you're moving your arms in it and it's assisting you, how is it sensing you moving your arm?
It's right underneath the chest panel because my arms are nowhere in those robot arms. Otherwise, I'd have to do a lot more finicky measuring and stuff like that. So, just this. That does cover. And there is actually a pair of joysticks right in the chest. And it's just essentially a box with push buttons around. So it can sense if I push the joystick on the left side, it pushes the left button, makes the arm go one way, makes the elbow bend, all that sort of thing. So when I am operating it, my arms are right in here. You know, pull the joystick up, bend the elbow, push the back of the joystick outwards, lift the arm, push the front of the arm, the front of the joystick, and twist the arm. I tried to make the motion pretty natural, but there is a bit of a learning curve with it. And the power source is actually nothing too fancy. It's just one of these standard 40-volt tool batteries. I would try the 80-volt setting, but unfortunately the motors I use are only rated for 12 volts. So as you can imagine, running them at 40 volts is already pushing their limits. Because, you know, if you run them too far and you're not careful, the linkage here on the end will actually fly right out and have to stuff it back in.
Can I ask quickly about the battery? So is that battery originally for like a piece of industrial equipment or like you know, drill or something, you know, something like that?
Well, I picked this up at Harbor Freight, so it's a tool battery. It costs like $100 for one of these, and unfortunately I bricked one, so that unfortunately brought the development price up. But as a whole, I probably have spent less than $1,000 on this thing.
Well, the nice thing about buying batteries that are replacement batteries for a product, whether it's like an electric scooter or a drill, is that it comes in with its built-in battery management. So while you might have wasted the battery, at least it didn't catch fire spontaneously. That's an advantage of buying those and paying the extra money over just a regular LiPo by itself.
Yep, pretty much what I try to do is use as many off-the-shelf parts as possible, because, you know, it keeps development time down and you can do the really fun stuff, which is, you know, making the power armor work the way you want it to. So there we go. And as I mentioned before, this wibbly wobbly material is not the final product. That's what I got. I started off making the dong piece to test that out and get my hammer from my workshop assistant here, and you can see it can take a beating pretty well, unlike, you know, that crap. So of course, because I was focusing on the aesthetics first, it's learning a lot about how the design and see how actually useful this design is, and it's lovely and complicated, but it takes a lot of effort. It would take a lot of effort to get all these complicated shapes, you know, in metal. So I'm probably going to be reducing it to something much, much simpler. And of course, there's the mystery lady right here. I affectionately call the workshop waifu. And it actually has a reason other than just being a weedy mess. It's actually figuring out how to control these heavy-duty motors using a computer, a Raspberry Pi. So I've got like some basic voice commands in there. We'll see if she'll cooperate. Gary. No, I don't think she's listening. Just like a woman. But really, it's just using servos to flip switches for reversal polarity of the motors, which is a pretty janky way. I could probably look into getting more elaborate and complicated motor controllers, but you know, those things are a little bit harder to find through normal routes, because a lot of this stuff I order off like Amazon and things like that. And really, she's a promotional tool. I gotta redo the traction system, and then I drive around at conventions and stuff, you know, like holding signs in her little hands and things like that. Gary. Greetings. There we go. She's giving a little bow. And that's actually using one of these heavy-duty motors in the torso, and, you know, being controlled by the Raspberry Pi. So having a one of these big chunky motors controlled by a Raspberry Pi opens up a lot of possibilities, like a more fine-tuned power armor control system, so it can use actual joysticks and do some fancy stuff with like having the arms move slower or faster, controlling, some pretty janky motor controllers to do that. And of course, make giant walking electrical PCs, which I'm actually working on. It's a bit of a work in progress, keeping it under wraps until I actually figure out how much it can weigh. Because the ideal would be to have a 500-pound machine with me inside, walking around, punching things. But it's pretty much nothing particularly useful. It's more for entertainment. Once you get entertainment and that whole revenue stream coming in, you can then focus on making stuff that could be, more practical.
Well, cool. I've got a quick question. First of all, I mean, this is fantastic. This is some of the most, in-depth workshop, like home workshop stuff I've ever seen. What kinds of manufacturing processes do you use to make these? You use a lot of 3D printing, any CNC machining, just like, cutting and welding material. Kind of what's your primary way of actually constructing these?
Well, I've got 3D printed parts for like controllers because I don't really trust 3D printed things for anything structural, probably because I'm old-fashioned. But a lot of it is actually using PVC, because that stuff is just like, giant Lego or something, just with stinky glue. Plus, you can drill it easily. It's easy to work with. The structural integrity is a little questionable, but it's surprising actually if you put in like a proper cross bracing and stuff, how much weight it can support. And I do have a welder, but I'm still getting the hang of figuring out how to use that, because it's one of those flux core welders, which is like a hot glue gun, and a welder had a baby. And, you got to get all the settings just right and hold everything just so. And with a welding helmet, it's harder than heck to see out of what it's actually building. So it's a learning curve. But I'm starting to look into using metal structure instead, because that would also, open up a lot of possibilities, and it would give the appearance of, oh, it's actually made out of metal instead of, plastic.
Yeah, absolutely. And then my other question for you was, do you have any good stories about like, lessons learned where you tried something one way and then that just ended up not working at all, and you had to really kind of change the way you were approaching it?
Well, when it comes to things of this scale, there is a surprising amount of leverage involved. Because, when you've got your motor's like let's just say 3 inches from the armpit joint, right? And then you got a 30-inch arm. Because of leverage, that's going to multiply the load on the end of your arm by 10 times, because, 30 divided by 3, that's a factor of 10. So you really got to look out for that leverage. And also, when you're building larger stuff, for it to cover the same distance as a human, it appears to move slower, because you got an arm twice as long. The elbow only has to rotate half the distance to cover the same distance the human would. So the larger something is, the slower it appears to move, but it's actually moving as fast as a human. So if you want something like twice as big as a human to appear to be moving the same speed as a human, it actually has to move twice as fast. So there's a lot of like hidden leverage and calculations that really make you scratch your head. And it's like, I probably never would have thought of that if I hadn't actually done it in real life.
Yeah, that makes a lot of sense.
That, no matter how much time and thought, I mean, most of the time you put too much time and thought into it, and you would have learned quicker just by doing it and finding out. Interesting. Do you have any plans to? I very much like the the keep it simple, stupid way of going about building a piece of large equipment, especially because safety is obviously a factor. And once you start introducing code, you introduce bugs, and bugs when you're trapped inside of a giant piece of machinery isn't fun. But do you have plans to, go forward to add a bit more in terms of sensors and software, so that your power armor might have a heads-up display or night vision, or something fun in that kind of vein?
Oh yeah, I did have an experimental heads-up display, which uses the Pepper's Ghost optical illusion, which is you got a screen right here, and then a piece of transparent plastic right here. The screen reflects on the plastic, and it gives like sort of a projection heads-up display. And really, carry right here, which is what I call this little robot because it's meant to carry my tools around the workshop, is an exercise in not only controlling the large motors, but also doing voice commands. So it could be like Iron Man, you can tell like the power armor to say gun down, it'll move like a big shoulder gun down into position, or you know, what's a day, and it'll tell you in like a computer generated voice. So this little robot right here, despite being a sort of anime themed nerd sort of wet dream, is actually represents the next stage in the mechatronics that I'm doing, which is integrating computer controls in, again, trying to do the simplest way possible, because this thing only has about 200 lines of code, but even so, I question whether it's got a machine spirit in there or something. Now, yeah, sometimes it acts in an unsurprising way. So when you have that going on with something this small, you don't mind it too much. But if it's something you're inside of, that's when things start to get a little worried.
That's a very smart strategy then, to have the two projects that allow you to, test and fully refine, your ideas before you go into before you step inside it. Okay. Any more questions? Or otherwise, Michael, I'll let you introduce our next speaker. We were meant to be having another participant at 1/4 but we were expecting them to be a no-show, and that's turned out to be true, which is just part of the process.
Yes, I think you're right. I think we've had a dropout. Thank you very much for your presentation. This has been great. Exactly the kind of thing we want to see in a community presenter. So thank you very much. Next up, we have Vasily coming up with RimBrain, which is a cloud platform for smart robotics. So Vasily, go ahead and take us away.
Yeah, hi. So I and my colleagues, we've been in computer vision for, 15 years, and last a few years, of course, it was about deep learning and standard computer vision pipelines when you annotate data, when you train some neural networks, and it works or not, sometimes doesn't work, and you need to retrain it all the time. And from that, usually it's so-called machine learning pipelines or flows that are used. And we started to think about the same in robotics, because in robotics, it's absolutely another story. You can, when you manipulate any object, you can see at the same time what on cameras, and actually those manipulating gives you enough information to train. So those ML flows for robots, they can be built on another idea, on another way, in another platform. And we decided to start a project, then a startup about that. And let me share my screen and do the presentation. How it works now. Yes, so now we are a commercial startup, but I still think we have something to share despite this with the community. So what we started to create, we wanted to create a kind of fast track for doing smart robots, when you need to do just a few things to make any robot work, usually with arms, of course, or on wheels. So a robot can be connected to our system, streams of this robot, then it is teleoperated purely remotely without any machine learning, computer vision algorithms. And then for the customer, it means that actually the robot can be wrapped up and sent to his customer with our supervision and our ML algorithm on board. So how it works, or it's very usual ML flow with a human in the loop, when firstly you control the robot remotely, then data is collected, then it's taken to train ML processors, and then those ML processors are used to control the robot. Probably the robot will be not 100% accurate after, but still, thanks to the cycle, in a few days, it can become very, very smart and very, very accurate, up to 99.95%, just thanks to this ML cycle with human in the loop. So what is under the hood in terms of backend system? Any robot is connected through WebSockets that gives some security to our solution. It's called a cloud solution, but of course with some voodoo spells from DevOps, it can be also local. Then messages from robots are sent to ML processors or to operators, depending on who requests. Everything is stored and monitored at the same time. So once supervisor controls, we store cloud machine learning services used to retrain neural networks. New weights are delivered to ML processors that can be located in the robot or in the cloud as well. And this allows us to bring some security to the system, to make it convenient through, for example, through an API for robot vendors, for robot creators. And then how it, but okay, it's better to show how it works. So we tried it on a few applications. For example, this warehouse application is very close to what Ocado had in the beginning. And here we have a video how the whole cycle of training was done for the robot. So firstly, you can connect to the robot or reconnect, doesn't matter, and show what to do with particular objects. For example, this is so-called dry groceries that are stored in some smart systems, like, for example, Ocado has. And you see that that we show boundaries of the object on this 3D scene, and then we show where to put it. So this is a classic bin picking and placing task, but it's done absolutely manually, and yeah, of course, remotely. Usually it takes not so long to get hundreds of examples, sometimes a couple of hours, and it's enough to reach, let's say, 99% of accuracy after the first training. So it's actually not so long. Probably training takes longer, sometimes, especially on weak GPU machines. Yeah, so after this step, we will go further to training and how the whole training can be launched. So here we see the robot, it's some sensors, configurations, we can send comments from that window. And here we pick the robot we need and filter some comments that were sent. For example, we are interested in pick up, put down comments, and we can add those comments with that particular visual context to the training data set. And all the data will be used for training in a few seconds. So here we created a data session, and the training session can contain a few data sessions just to normalize effect of each data session. For example, it can be new types of objects, it can be a new environment, new light conditions, and so on. So here we just add a few data sessions to the list and start the whole training. And yeah, it's important to balance the data on this stage in the right proportion. Then Apache Airflow is used to start training all neural networks. In this case, it was 3 neural networks. Yeah, and here it's usual losses that are going down in an hour or two, and all neural networks are trained. And then with these new new weights, we can try an automated mode. Here, choose for that we need to choose a new task with new weights, and then it works. In this particular case, we had pace of picking about 10 seconds per one peak, or I don't know, maybe, yeah, 10. As you see here, picking is also optimized, but it's done not by a neural network. It's just some greedy mathematical algorithm based on depth map taken from 3D camera. What else here to say? Yeah, and after 4 or 3 training cycles, it was 95% of successful picking rate. That is super, actually, for such tasks. So this is how training. It's how training works. I stop sharing. Give me a second. Yeah. And the same we had for machine tending. It's another example where again it's a classical case as bin picking. It's a machine tending case, but it's, as you will notice further, it is done in a very tricky way. So firstly, it never gives up. So even in case of some problems, it is trying to continue. And as you see, parts can be flipped, or they can be brought back to the bin, for example, and in case of some problems. And this also was done in the same way. So it was trained. It was not programmed. That is maybe the most brilliant, that even such conditional things can be trained, but not programmed. So it gives actually more. It's easier. It is faster, and at the end, it is even more reliable when it's trained upon some neural networks than programmed by some programmers. So yeah, it's a very long video actually, so I will skip this and go back to the presentation. Yeah. So yeah, and it took for us 1-2 weeks usually to make a new case. And some 3D printing actually takes longer than training, because all those tips are very specific for each task. For example, it could be magnetic part, or suction cup, or fingers. Anyway, 3D printing always involved. So how it was done for the first case for groceries. Actually, when you send a command, you have a visual contract, that is an image, and you choose a picking point and you show boundaries, and the height of the object. So actually, it's enough to train 3 convolutional neural networks based on that: central point, segmentation of upper edge, and estimation of the object height, depending. It's a hidden parameter, but we just can remember the height of this particular object. And then those 3 neural networks are inferenced, and it works autonomously. So here you see a GB frame and depth map or depth frame for a particular case. So what is even more fascinating for me, how sequences of comments can be trained. So we can treat comments, sequences of comments as sentences with words in it. For example, pick place. It's one comment with some parameters. We call it embedding here. Then, okay, something went wrong. For example, we need to pick and place it again. Then we flip it, and then we send it to machine. And for example, this last comment is not known at this stage, so we need to predict. And it is very similar to a classic task in machine learning, predicting the last word or the next word. When you mask, so you have an input without the last word, and you have an output where this word is presented. Then it's a pure NLP task. Here we also used visual context, but not as a whole frame, but as a set of points to pick, and for example, point where to start flip and where to stop flip. So it was 3 channels, and to compress it into an embedding code, we actually trained something similar to autoencoder with encoder and decoder to reconstruct those points. And so this way we got 32 components vector of embedding that described these picking points and points where the flip started and where the flip stopped, for example. And the same embedding was used for any comments. Thanks to that, we could train pretty tricky, but still not very difficult LSTM neural network, conditional LSTM, where this visual context was used as a conditional vector to predict the next word, the next comment. So it's, yeah, and also I have a video, I mean, not perfect, but still how it was shown in VR in case of this industrial application. So firstly, we pick and place a part from the bin to some surface, for example, flat surface where it can be flipped. Then if it is required, we flip the part, and so we just show, so it's called shift here, how it must be flipped, as you see the part in the right place now, in the right orientation now. And the last comment was just actually pre-programmed in some way, so we don't show how to pick it up accurately to the machine, but still it is placed in the machine or kind of machine. Yeah, so here how those sequences were shown. Okay. Yeah. And basically, I'm close to the end of this presentation. So I showed and told how it was trained for one type of application, another type of application, and what we are trying to do next, to teach next. Now we are going to work with mobile robots, and so when someone from Ocado or AutoStore says they have a micro-fulfillment solution. No, actually, this will be a micro-fulfillment solution in Stavanger in Norway, where we ordered a robotic arm to pick donuts and to place them into delivery robot. Capra Robotics, they have these fancy 4 wheels robots for outdoor, and we will apply the same approach for training how outdoor robots can drive around. It's not so actually difficult, because when you drive remotely, you show the trajectory at the same time, and you also can remember how to react on some obstacles. For example, if you have a person in front of you, how you can drive around this person. And this will be next, I hope, story next year for Reddit. And we will try to do this, because actually it is super profitable. Now in Norway, people are super expensive, and for example, 4 shifts of labor force costs like 15k euros per month. But at the same time, as you know, mobile robots and robotic arms are becoming cheaper. I mean, 1 month can cover 1 robot. So that's all.
That was really, really interesting. I really enjoyed that. I really enjoyed the presentation, the slides. There's a lot of different concepts and information that's going on, and I think you did a very good job of getting through it all. Also, opened my eyes to, often people, when we talk about robotics, we're worried. We talk about how this will put people out of jobs, and that is true. There's a part of it, but there's also the other part of it of creating new jobs. And I didn't realize there's now going to be a job for people who own VR kits at home to help train these robots. And they could be doing that from the comfort of their living room and getting paid for it. That's an interesting possibility.
Yeah, this is it is true. And actually it gives some opportunities to people to find jobs, I would say. And training teaching robots, I think it's a good thing for future. I mean, actually, you said that it takes jobs, but not. Of course, it increases the efficiency all the time. So no one is fired.
Would you rather train the delivery robot or do the deliveries yourself?
Yeah, and of course, one guy can supervise like 4-10 robots. So that's why it is becoming more efficient. So you have a new type of business, you have a new business, a new service. For example, in Norway, they, especially in Stavanger, they don't have those to-door delivery, because it is super expensive. No one is going to get so low salary or to pay so much for delivery. Okay, I will go and grab my donut in the morning by myself, because otherwise it will be 10 euros for this delivery. And this service is appearing after. So once you have new opportunities, you open new business or you scale your own business. For example, you can build a new strawberry farm, adding it to that you had, and you will hire robots, but you will not fire people at the same time. And besides, you will be more effective. You will be able to pay more for the same people, for the same job, for example, or you will be able to make their work not so boring, because robots will take this part of job. So in real scenarios, I haven't seen that robots took jobs from people, but it gives some new opportunities for companies to make money, to be more efficient in the market, and to pay salaries thanks to this.
Okay, I'd like to ask one more question, and then there's quite a few very good questions from the comment section. I'll let Michael handle those. That's okay, Michael. So the other thing is, you mentioned am I pronouncing it right? Stavanger, Norway, Stavanger.
Stavanger. I don't know.
Okay, right.
Yeah.
Best I can. So Is that so? It's part of your business model then to very, target a very specific city then as part of your business structure. So is that something where you kind of partnered with like the local city council? How does that kind of a thing? How do you talk with a town and say we'd like to put robots in your town?
Yeah,
how does that conversation go?
Actually, this works. I mean, you just pick the most expensive town in the world. You go to the communa, it's so-called communa, and start to talk with them. Okay, we can bring some robots, we can bring some new services into your area, and it makes a lot of economical sense. So you probably know this curve, how robots are becoming cheaper and cheaper each year, and that labor force is becoming a bit more expensive each year. And in different towns, different countries, actually those intersections happen in different times. So in Stavanger, it happened, I don't know, 2 years ago, definitely. So it creates some demand. So it's exactly how it works. And in cheap countries, it is more difficult to implement new robotic systems. Actually, you don't have this demand. All unit economic doesn't work. So yeah.
Very interesting. Thank you. That's very insightful. Really appreciate your answer there. Okay, I'll pass over to Michael to answer some questions from the audience.
Yeah, so thank you again for such a great presentation. We have a few questions from audience members. Do you have any sort of motion planning in the loop that takes care of obstacle avoidance?
Yeah, it's actually in that application with groceries, there was path planning, but for the industrial case, we actually didn't do this because all approaches were vertical, and thanks to that, we could just forget about collisions, and because they don't happen if you pick parts correctly. But in general, yes, it's a very usual story, and actually, it's a very difficult story, I would say, in robotics now with arms, because path planners are not so fast. So you need, 1.5 seconds, for example, even on a good CPU to plan it with some obstacles on the scene. And I would say that it's a good story to develop in future, so make it more trainable, for example, and to apply a lot of efforts for us, for other teams in this field, because it's very old school now, I would say.
Yeah, absolutely. Yeah. How do you achieve the robot calibration with the camera? Is it an automated process, or do you manually control the calibration between the robot and the camera?
We had a setup, as you notice, where a camera is installed in one place, not on the robotic arm, but outside of it. And this is the simplest case to calibrate. You just show by a tip of the robot where some tags are, for example, like AR tags placed around on the scene, and you just place the robot arm in this particular place one by one, and at the same time you just check where they are through the camera, and solve a very simple mathematical task, calculating a matrix that brings one coordinates and orientations to just coordinates to other coordinates. And it allowed us to, so if you notice, it was very, very accurate 3D scanner, like 0.2 millimeters. We also, of course, worked with RealSense, but for videos, we always used a good 3D scanner from Zivit. And this allowed us to achieve 0.5 millimeter in the calibration.
Okay, great. Yeah. it looks like you're occasionally scanning with some kind of structured light from the camera in order to kind of like identify, the task. Does this mean that you're not using the camera outside of this? Like, are you still receiving feedback from the camera in between these structured light scans? Or are you just kind of scanning once and then using that image data to move stuff around and then scanning again?
Yeah, in this case, in videos, it was not a video stream, but more I don't know, photo stream. So
Yeah,
it was taken from time to time, as you noticed, and so it was so-called temporal pattern approach for 3D scanner, when you have different light patterns projected one by one on the scene, and based on that you distinguish what, so you can distinguish lines. Okay, it's a long story, but it's just one of approach. So there are structural light, for example, for real sense. There are cameras with structural and temporal patterns, and that one was temporal light. It allows to get higher resolution in depth map, so up to 2K, yeah, resolution.
Okay, great. Yeah. Do you incorporate sensor feedback into your models, or is your system more aimed at generating high-level sequences of objectives that can then be executed by like non-machine learning systems?
Now we remember, so we store comments from operators. We don't, so at the same time we keep sensors, for example, arm position and so on, and in some applications it can be used and it will be used, but particularly here we just used what operators show, so it was like a simulation learning or some so-called imitation learning, actually. So we are trying to do similar to what operators show, and we didn't use sensors at this stage, except only if it was picked or not. Of course, we used a sensor, but it was a vacuum sensor to understand maybe this object was dropped and we need to try one more time. But in general, not on this stage, correct?
Yeah, okay. Is there any scope of automatic calibration from the video feed, like placing bins under the camera and then an automated routine taking care of the calibration from there?
Yeah, we had an automated calibration for real sense, for example, because it was not so accurate. We could live with 3 millimeter of accuracy, and in this case, an automated approach worked good. But for example, for Zivit with a high accuracy camera, we actually left a manual calibration procedure. Bins were detected and used in building a task. So we divided the whole configuration into two parts. One is robotic configuration, so I mean configuration of a robot without its task. Then you have a task. For example, you put a bin and you set a task, take parts from this bin, and in this moment, this bin was detected. So in automated mode. So some parts of that procedures were automated, some not.
Okay, that makes sense. And then kind of our last question, I think, is do you do any kind of computations on how to pick up objects that aren't flat, that don't have a flat surface?
So not. Could you comment again?
Yeah. So a lot of your examples that you showed were kind of like boxes or stuff with lots of very flat surfaces that are kind of nice, quote unquote, right, to pick up with a vacuum pump.
Yeah,
You
I
guys
got it.
not like that. Okay. Yeah.
Yeah, actually, the picking point was not in 2D, but in 3D plus orientation. So when you show in VR how to pick something, you have a 6D vector, like orientation and vector, and it worked. It works, and actually. Obstacles, checking obstacles, space planning was about exact this task, because when you have everything vertical, you don't need any space planner. No obstacles will be on your way. But for some other orientations, you always have a chance. And as you saw in Ocado, for example, videos, they approach some objects not vertically, and because of that, collisions are becoming possible, and that's where exactly the path planner started to work. And we had that training pipelines, not in the video, but actually it was not so necessary. I mean, you have like a lot of new challenges. You have not 95% of accuracy, but 99, for example, 2 or 94% of accuracy, because it's not so simple for neural networks, for example, to estimate orientation. But so you need to estimate point plus orientation, and your chances to make mistakes are becoming higher. Chances to have a collision are becoming higher. So in real practice, when you really need high accuracy, just keep it vertical, and don't try to. But of course, the pipeline allows us to do this, and we had this in our demos. But actually, make it simple. Always make it simple.
That makes sense. Keep things nice and simple. No spheres, just kind of flat surfaces. Makes sense.
Yeah, even when we talked about donuts, for example, it's actually very complex to grasp it. You need some special tips and some flexible, for example, and we ended up with placing each donut in a box for it. And it's becoming super simple in this case. I mean, the robot is becoming twice cheaper, and the only thing you need just to place a donut into its personal box, and it's not so expensive actually. And so really,
that makes sense. That makes a lot of sense. Yeah. And then I think we have time for one more question then, and it's.
I was going to say that question is one where really they should get in touch with you directly, or someone looking to see what your industry collaboration for PLC is. And I said that's something where they should probably just get in touch directly and find out a bit more. They can get in contact with that. Thank you very much, Vasily. That was really, really good. And I won't say I'm glad that we had no shows that have given you extra time, because it would have been nice to hear from their projects too. But I'm glad we've been able to go in detail for this, because it really has been interesting. That concludes, everyone. A remove spotlight. I think will be put back onto me. Oh, I'm going to spotlight myself. Thank you. So that concludes our first session of this weekend, Industrial and Automation. In approximately 2 hours from now, that is 2 p.m. Eastern Daylight, 7 p.m. British Summer Time. Do the math for where that is in the world for you. We'll be returning for our second session on a different live stream. You can find all the links on the YouTube channel, and that will be for mobile robots with a keynote from the University of Lincoln, Robots in the Wild. So take a couple of hours, get some food, a bite to eat or something like that, and we will see you then. All the best.
Yeah. Bye.